So just like we had the notion of local optimality for unconstrained problems, we also have the notion of local optimal solution. So a point x star is locally optimal if x star satisfies all constraints. That means it belongs to this set feasible region R, and there are no other points in the neighborhood of x star that are feasible and also have lower objective value. So for example, let's say minimize x1 square subject to x1 between 1 and 2, x1 equal to 1 is a local optimal, is a locally minimum point. Notice that if I go below x1, my objective function will actually be better, but I will be leaving the feasible region. So geometrically I am in only one dimension. So I am constrained to be on this line segment, and my function value is going up from 1 to 2, and if I didn't have the constraint, then I might have found better solutions, but because of this constraint I can draw a neighborhood around 1, and I can see that in this neighborhood all the feasible points will have value higher than what I have at x equal to 1. So just like we had the notion of a global solution or a strict local solution or strict local minimum, similarly we can have corresponding definitions for the constrained case also, very similar to the unconstrained case, but the only restrictions now we add is that we have to look at the intersection of the neighborhood with the feasible region R. And this can lead to some very interesting points which may not have any neighborhood at all, but may still be feasible, in which case they would be locally minimum. So let's come to some of the transformations which allow us to model constraints which are not really in the form that we had written earlier. So recall that our problem is, so again the general problem is of the form minimize f of x, ci of x equal to 0, I equal to 1 to k, and ci of x greater than equal to I equal to 1 to k plus 1 to k plus l. Sometimes it might be easier to use the notation that I is in the equality constraints denoted by set E, and I is in the set of inequality constraints I for constraints that have greater than equal to sign. So if I have a constraint which has a less than equal to sign, so for example, if we have a constraint, let's say x1 square minus 3x1 x2 plus 7 less than equal to 0, then I can always multiply this constraint by minus 1 and get a problem in the form that I want. So these two constraints are exactly same, minus x1 square plus 3x1 x2 minus 7 greater than equal to 0. Okay, so multiplying a constraint expression by a negative number leads to a change in the sign. So this is a very important property. This will be used again and again to bring the problem into the form that we like. Okay. Another transformation that we typically use is to convert inequality constraints to equality constraints and vice versa. So again, let's look at an example. Suppose I have x1 square plus x2 square less than equal to 7. Then I can add a new variable to make it an equality constraint. So I can say that x1 square plus x2 square plus x3 equal to 7, and x3 greater than equal to 0. So I need both constraints to be equivalent to my earlier constraint, and you can see that any point which is feasible for this has a corresponding feasible point here, right? So for example, 0 0 is feasible here, and 0 0 7 is feasible here. Okay. 2 comma 1 is feasible here, 2 comma 1 comma 2 is feasible here. So these constraints are equivalent, and if I optimize my function over this set, I will get the same solution if I were to optimize my function over this set. Okay, so at least the value of the program or the optimization problem will come out to be the same. Okay, so so this variable is, which we have added ourselves, it was not there in the original problem. We have added it to transform it into the form that we like, and this is sometimes called a slack variable. So slack variables are variables that we add to less than equal to constraints. Okay, if I have a greater than equal to constraint and I want to make it an equality constraint, then we take away a variable called a surplus variable. So for example, if I have, I can rewrite this as minus x3 equal to 1, and I can even take 1 to the other side and say, and x3 is a surplus variable now. Of course, this is incomplete. I need one more constraint which enforces x3 to be more than 0. So notice that I can rewrite my constraint as an equality constraint, but I will still have some inequality elsewhere. So I cannot really eliminate these inequalities. So even if I transform this into an equality type, I will still have some inequality on bounds, in terms of bounds on variables. So these inequalities can't really go away. Okay. On the other hand, if you have a equality constraint, I can rewrite this in terms of inequality constraints only by saying that this is greater than equal to 0 and also less than equal to 0. So if some expression is both less than equal to 0 and greater than 0, so then that means it must be equal to 0. And then I can multiply this second equation by negative 1, and this would become minus plus greater than. So if a problem has some equality constraints, I can always convert them back to an inequality form. However, if I have inequality constraints, then usually it is not possible to eliminate all inequalities. I will still have inequalities in terms of bounds on variables. So those can't go away. Okay. So that is somewhat important when we talk about methods to solve these problems. One can be very creative and try to remove inequalities by instead of using some slack variables or surplus variables, I can use some nonlinear functions. So for example, if x1 is suppose I have a constraint it says x1 should be less than equal to 10 and more than 7, then I can rewrite this as x1 equal to 7 plus 10 minus 7 times sine square y1. We know that this expression is always between 0 and 1. So x1 can take values between 7 and 10 only. So no slacks or surplus variables required. So this might look very enticing in the sense that I have not added any more variables in the inequality form. However, I still have an additional variable, and I have a nonlinear term now instead of something which was earlier very simple and linear. So these transformations are usually not recommended. Because they make the problem more difficult to solve rather than making it easier. Also, sometimes it is very tempting to convert a constrained problem into an unconstrained problem. So for example, if I have a problem like minimize x1 square subject to x1 greater than equal to 0, I can remodel it as minimize x1 square subject to x1 equal to x2 square and then change the objective function to x2 to the power 4 and then since the x1 is only dependent on x2 and doesn't appear in the objective function, I can just drop it off, solve the unconstrained problem and get x1 from x1 equal to x2 square. Okay. So these types of transformations are valid, so technically valid, but again not recommended because once we start solving this problem, we might have more difficulties in solving as compared to solving this. So for example, the Hessian or the second derivative of this function at origin is 0. That means I will not be able to identify whether my solution is actually a local minimum or a local maximum. Okay. There's another example very nicely given in the book which tries to minimize x1 minus 1 whole square subject to x1 greater than equal to 0. One might be tempted to transform this problem into an unconstrained problem by just replacing x1 by x2 square and noting that x2 square is automatically always positive. So x2 square minus 1 whole square, and now I'm minimizing over x2. So again, if I look at the critical points, then x2 equal to 0 becomes a critical point which earlier was not. Okay, so x1 equal to 0 is not a critical point, and it is possible that when I solve this problem, some algorithm may actually converge to x2 equal to 0, which will be a poor solution as compared to what we might get by solving this constraint problem. So sometimes it is beneficial to eliminate some constraints and reduce the problem to an unconstrained problem, but many times it might be counterproductive to make the problem more complicated by adding some weird nonlinear terms so as to eliminate the inequalities, or to make the function or to make the problem unconstrained. Okay, so this is something which usually falls under the case of modeling things. We will not go too much into the details of these modeling tricks and why they are useful or not very useful, but rather we will look at some more terminology of these constrained problems.